The next lesson in our periodic table and bonding unit is on the octet rule and ion formation. Here are our learning targets for this lesson. We're going to do these first two here together. We want to be able to state the octet rule and apply it to ion formation, and also to be able to differentiate between cation and anion formation. So first of all, the octet rule. The octet rule simply says this: atoms are most stable with a full outer energy level. If the outer energy level is the first level, then that's 2 valence electrons. That's as many electrons as you can put in the first energy level. If the outer energy level is any other level other than the first, so second, third, fourth, etc., then we're talking about 8 valence electrons. This is actually why it's called the octet rule, because octet referring to 8. So all other levels, if the outer energy level is not the first level, then it is full with 8 valence electrons. Atoms will always gain, lose, or share valence electrons to achieve their octet. In other words, they do this in order to become the most stable they can be. Let's look at some definitions here. First of all, the definition of an ion. An ion is simply any charged atom or group of atoms. A cation is more specific. That is a positively charged ion. Whereas an anion is the opposite. It's a negatively charged ion. Now we have the term monatomic ion. The prefix mono, as you can see here at the beginning of this term, means 1. So when we see monatomic, it literally means one atom ion. So a monatomic ion is simply an ion made of one atom. We're going to now look at how these monatomic ions form and why they form. First, we'll take a look at cations. Recall, cations are positively charged ions. So metals, they lose valence electrons to form cations. Let's explore why this is. Recall, metals are found on the left side of the periodic table. Let's think about group 1 ions. So any element in group 1, so we're talking hydrogen, lithium, sodium, etc., they're always going to have a 1 plus charge on their ion, and here's why. Let's take a look at lithium. So lithium has 3 protons and 3 electrons. Recall its atomic number, which is 3, gives you the number of protons, and if it's neutral, it also gives you the number of electrons. Now, because lithium is in group 1, I know one of those electrons is a valence electron. Recall the group number gives you the number of valence electrons. And that one valence electron is in the second energy level. We know this because lithium's in the second period. So here would be a picture of lithium. So really what we're looking at here, this gray circle in the middle represents the nucleus, and that's where all the protons and neutrons are. And those we're really not concerned with our discussion here. And then it has 2 energy levels. The first energy level with 2 electrons, denoted by the black dots there. The second energy level with the 1 valence electron. So what lithium will do is lithium will lose that 1 valence electron. And the reason why it does that, you can see it happening in the picture here, is now its outer energy level is the first level, because there are no electrons in the second level. And now that the outer energy level is the first level, it has a full outer energy level. Recall, if the first level has 2 electrons, then it's full. And so lithium is most stable whenever it has just these 2 valence electrons in the first energy level. Now, because it lost an electron, it is now positively charged. You might be wondering, how is it positively charged if it loses an electron? Should we call that negative? Well, if you think about what the electron is it's a negatively charged particle. And so now it still has 3 protons, but it's still lithium, but now it only has 2 electrons. And as we know, protons are positively charged. If protons are positive and electrons are negative, which they are, and we now have more protons, that's going to make the ion positively charged. The fact that there's 1 more proton than electron means it will have a 1 plus charge. So the net result here is we've gone from a lithium atom, which we would just write with the symbol Li, to a lithium ion, which we'd write either with the symbol Li and then the superscript 1 plus, or we would just write it the superscript with just plus. If there's no number there, it's understood to be 1. So let's think about sodium. Sodium's also in group 1. It's just like lithium. It's also in group 1. So let's see if it's still going to have a 1 plus charge. So sodium, if it's a neutral atom, has 11 protons and 11 electrons because it's atomic number 11. And note, because it's in group 1, it still has one valence electron. Now this valence electron, unlike lithium, will be in the third energy level because sodium's in the third period. So if we look at a picture of sodium, it might look something like this, where the symbol here in the middle represents your nucleus, your protons and neutrons. And then we have 3 energy levels, 1, 2, and 3. And then the first energy level has 2 electrons, the second has 8, and then the third has 1 for the 1 valence electron for a total of 11. So sodium, just like lithium, it's going to lose that outer energy level electron. So it's going to go from 3 energy levels to just 2. And now notice that second energy level, which is now the outer level, has 8 electrons. Well, that makes it full, because any energy level, unless it's the first, if it's the outer level, is full with 8 electrons. So just like lithium, sodium will lose 1 valence electron. This will now give it 11 protons because it still has 11 protons, it's still sodium, 10 electrons because it lost 1, 8 of which are in the second energy level, meaning its outer energy level is full. So the net result here is we've gone from a sodium atom, oh, that should say sodium, that's a typo, not lithium. We've gone from a sodium atom to a sodium ion. And again, notice the way we write the formula for the ion, we still use the symbol Na for sodium, and then we either put 1 plus or plus as the superscript there to show that it has a charge to it. So let's look at a different group. Let's think about a group 2 metal. In this case, let's think about magnesium. Well, because it's group 2, we know it's going to have 2 valence electrons. Now, magnesium is atomic number 12, so it has 12 protons, 12 electrons, and it does in fact have 2 valence electrons. So a picture might look something like this, where we have our magnesium atom here on the left, and again the middle circle there represents the nucleus. Then we have the 2 electrons in the first level, we have 8 in the second, and then 2 in the third, because it has 2 valence electrons, for a total of 12. So instead of losing just 1 valence electron, magnesium is going to lose 2, because if it loses these 2 valence electrons, it will now have a full outer energy level in the second level, because that would become the outer energy level. So if it loses 2 electrons, it will now have 2 more protons than it has electrons. It's still going to have 12 protons, but now we have the 10 electrons, 8 of which are in that second energy level. So we've gone from a magnesium atom to a magnesium ion. And notice when we write the formula for the magnesium ion, there's only one way to write it, because it has a 2 plus charge, because it has 2 more protons and electrons. So when we write it, we just write the symbol for magnesium, Mg, and then a superscript, we write 2 plus. Do note that it is written 2 plus and not plus 2. So what we've established so far is that all group 1 metals have a 1 plus charge in their cations. Group 2 metals are all 2 plus. There are other metals that only form one monatomic cation. Those would include aluminum, which is always 3 plus, silver, which is always 1 plus, zinc, which is always 2 plus. These here you will probably need to work to memorize, okay? Because we do use them quite a bit. So that being said, the fact that we do use them a lot means that you probably won't have to work that hard to memorize them, because you'll just know them naturally as we use them. And the other thing I wanted to bring up here is that notice now we have this next point, is that most other metals, they actually form multiple ions. In other words, we can't just say an aluminum ion or a silver ion for these others, because they can form multiple charges. So for example, copper is either 1 plus or 2 plus. Iron is either 2 plus or 3 plus. Vanadium is 2 plus, 3 plus, 4 plus, or 5 plus. Now you don't need to know what these are. You don't need to memorize these. The point is just that outside of group 1 and group 2, and then these 3 metals here, aluminum, silver, and zinc, those other metals, they form multiple charges in their cation. Alright, so we've looked at cations, where metals will lose electrons to form those positive charges. Now let's look at the opposite. Let's look at anions. So nonmetals, they will gain valence electrons to form anions. So for example, halogens, and recall halogens are in group 17, they're always going to have a 1 minus charge on their ions, and let's see why. Let's take a look at fluorine. So fluorine is atomic number 9, so it has 9 protons and 9 electrons. And the fact that it's in group 17 tells us it has 7 valence electrons, which are in the second energy level because it's in period number 2. So here would be a picture of fluorine. So notice again that middle circle representing the nucleus, and it has the 2 electrons in the first level, and then it has 7 in the second for a total of 9. So it has 7 valence electrons. Now you might be wondering, well, why doesn't it just lose 7 like the metals did? Well, it could lose 7 electrons. That is possible, but there's always another option. The option being to reach its octet by gaining instead of losing. Well, if it gains electrons, it only needs to gain 1. Because notice, if it gains just 1 single electron, it now has 8 electrons in its outermost energy level, making it most stable. So that is by far easier to do, gaining the 1 electron as opposed to losing 7. And so nonmetals, because they already have lots of valence electrons, they tend to gain these electrons whenever they form ions. So we can see that the fluorine gains the 1 electron to go to the second energy level to fill its octet, making it the most stable it can possibly be. So it now has 9 protons and 10 electrons, 8 of which are in that second level, filling that octet. So what we've gone from now is a fluorine atom, where it's neutral, we just write it as F, and now we formed an ion. And note the name of this. We do not call it a fluorine ion. It is called a fluoride ion, IDE. With these monatomic anions, recall the anions are the negatively charged ones, we always drop the ending of the element name and add IDE. So it's not a fluorine ion, it is a fluoride ion. And you can see how the formula is written there. We still use the symbol F, and then a superscript, either minus or 1 minus, to indicate the charge. Again, recalling that if there's no number there, it is understood to be 1. So group 16 nonmetals, this would be oxygen and sulfur and other nonmetals, group 16, they're always going to be 2 minus, and we'll see why here. Let's just consider oxygen as an example. So oxygen is atomic number 8. It has 8 protons and 8 electrons. We know it has 6 valence electrons because it's in group 16, so that has those elements have 6 valence electrons. So a picture of oxygen would look like so. You can see it looks very much like fluorine, except it has just 6 electrons in its outermost level as opposed to 7. And like fluorine, it's going to tend to gain electrons to fill its octet. Now in oxygen's case, it's going to need to gain 2 electrons because it only has 6 electrons in its outermost level to start with. So if it gains 2 electrons, you'll notice now that it has a full octet. These 2 electrons here that are showing up in blue that were gained, those have been gained, and now it has a full octet. So it's the most stable it can possibly be. Now because it gained those 2 electrons, it now has 2 more electrons and protons. And because it has 2 more electrons and protons, it will have a 2 minus charge. Note how we write the formula, where we have the O for oxygen, and then a superscript 2 minus there. And then the name of it, again like we said before, with these monatomic anions, we do not use the element name, we use the IDE ending with it. So it's not an oxygen ion, instead it's called an oxide ion. Alright, lastly, group 15, as you might guess, they are going to form ions that have a 3 minus charge. For example, let's take a look at nitrogen. So nitrogen has 7 protons and 7 electrons. It's in its atomic number 7. And it's in group 15, so it has 5 valence electrons. And here you can see a picture of what nitrogen might look like, where we have the nucleus there, and with its 7 protons and 7 neutrons, and then we have 2 electrons in the first level, and we have 5 in the second, for 5 valence electrons for a total of 7. So nitrogen will have to gain 3 electrons in order to form an ion, because it needs those 3 electrons that are showing up there in blue in order to fill that octet. And so because it has to gain 3 valence electrons, its charge will be 3 minus. So a nitride ion, that's what we would call this, a nitride, IDE ending, would have 7 protons and 10 electrons, thus giving it a 3 minus charge. So a point I wanted to bring up here would be this question here, is that noble gases, they rarely form ions. And I want to ask why. So just pause the video, think about that. Think about where the noble gases are on the periodic table and ask yourself, why do they rarely form ions? Okay, so you've had a chance to think about it, and hopefully what went through your head was something about the number of valence electrons that noble gases have. Recall that noble gases have 8 valence electrons, or in the case of helium, it only has 2 valence electrons, but remember, those are in the first energy level. So noble gases, whether we're talking about helium with its 2 valence electrons, or any of the others, neon or argon or xenon or any of the others, they have a full outer energy level already. So they are already the most stable they can possibly be. In other words, if a noble gas were to form an ion, it would actually become less stable, because when it gains and loses electrons, either one, it's going away from its octet. And if it loses its octet, it actually becomes less stable. So this is why noble gases rarely form ions. Now you can get noble gases to form ions if you hit them with enough energy. Anything can form an ion, but for the most part they really don't. Alright, so far in this lesson we've looked at these first 2 learning targets. We can state the octet rule and we can apply it to ion formation, and we have differentiated between cation and anion formation. The next thing we want to do is we just want to take what we've learned and we want to predict the charge on monatomic ions. So to do this, I just have a couple of examples to start. So for each of these, we're going to determine 5 different things. We're going to determine the number of valence electrons the element has. We're going to state if the element will gain or lose electrons when it forms an ion, and how many. We're going to determine the charge on its ion, and we're going to give the formula for the ion, and we're going to name the ion. Alright, so the first example here is phosphorus. Well, for phosphorus is in group 15, and so as far as the number of valence electrons is concerned, that would be 5. Group 15 elements have 5 valence electrons. Will the element gain or lose electrons whenever it forms an ion, and how many? Well, the fact that it already has 5 valence electrons means it's probably going to gain electrons. And it will have to gain 3, because if it gains 3 electrons from the 5 it already has, that will get it to 8. The charge on its ion, part C here, the charge on its ion. If it gains 3 electrons, it will now have 3 more electrons than protons, so its charge will be 3 minus. The formula of the ion would then be P3 minus, with this 3 minus as a superscript, and then the name of the ion would be the phosphide ion. So here you can see the answers. Again, just to review, phosphorus, group 15, so 5 valence electrons. It's going to gain 3 electrons to fill its octet, which means it will have a charge of 3 minus. Here is the formula, P3 minus with the superscript there. And then the name would be the phosphide ion. Notice it's not the phosphorus ion. We use the IDE ending. Alright, one more example here before I want you to try it on your own, and that's for strontium. So strontium is in group number 2, so it's going to have 2 valence electrons. And the fact that it has 2 valence electrons, meaning it means it will likely lose electrons to form its ion. It will lose those 2 valence electrons. So if it loses 2 electrons, it will have a 2 plus charge, because it will now have 2 more protons than electrons. The formula of the ion would be Sr2 plus, and the name would just be the strontium ion. So here you can see the answers, where we have 2 valence electrons, because it's group 2. It's going to lose those 2 valence electrons when it forms an ion, which will give it a 2 plus charge. Its formula then would be Sr2 plus, and we would call it the strontium ion. Alright, same question here. I'm going to give you an element. I want you to determine those same things from the previous slide. This time though, once you see the element, please pause the video, try it yourself, and then resume playing the video to see how you did. So the first one here is iodine. Please pause. Alright, so you've given it a shot. Hopefully you've come up with the following answers. Iodine is in group 17, so it will have 7 valence electrons. If it already has 7 valence electrons, it just needs to gain 1 in order to form an ion, so it will likely gain the 1. And if it does gain 1 electron, it will have a 1 minus charge, making its formula I minus, or you could write I1 minus there. And the name for the ion would be the iodide ion. Again, notice the IDE ending. We use that anytime we have a monatomic anion. Alright, next one is sulfur. Please pause the video and try it on your own. So you've given it a shot, and hopefully you have the following answers. Sulfur is in group 16, so it has 6 valence electrons. The fact that it already has 6 means it only needs to gain 2 electrons to fill its octet, so it would likely gain the 2. And if it gains 2 electrons, its charge would be 2 minus, making the formula for this ion S2 minus. And then the name for it, again, like the last one, it's a monatomic anion, so we're going to use the IDE ending, so that makes it the sulfide ion. Next one, rubidium. Again, pause the video. Hopefully you found rubidium on the left side of the periodic table and came up with the following answers. So rubidium has, hold on here, I did not do this correctly. Rubidium's in group 1. So we're gonna change these answers here as you listen. Rubidium has 1 valence electron, so it would lose just the 1, and it would have a 1 plus charge. Thus, it would be Rb plus or Rb1 plus, and it would be called the rubidium ion. My apologies there. Alright, so in this video, we have stated the octet rule and applied it to ion formation. We have differentiated between cation and anion formation, and then we have ended by predicting the charge on monatomic ions.